Good morning. So, lab 10 today. Yeah, sometimes forget that we are behind lab 10, and last lab is right before the Thanksgiving break, 23rd. And I think Thanksgiving break is till Sunday, which will be November 28th. So we have 2 more labs left. We're probably going to discuss the final exam next week. You know, what's going to be in there, what labs you need to focus on and all that, the format, what kind of questions will be there. So all of that will be discussed next week. It's usually pretty much the same every time. You know, you got, it'll be worth 100 points. There will be might be some multiple choice questions, and everything that will be there, you would have done that in the lab. So there won't be something, you know, anything new there. Everything's from the lab. Focus on the post-lab questions, all those things. But if you've done all the labs, there should be no problem. You'll get around 90 minutes to do that. I'll give you like 15 minutes extra to take pictures, turn your work, you know, upload it to Blackboard. So, but the labs, there are some things we usually do not give you in the exam because some things take time. But everything, you know, you won't have to do anything experimental. It's just everything will be just theory based on the lab. So you won't have to create circuits or anything. Okay. Lab 10, I uploaded it. And this is RLC circuit. Now, I think just check. That's labs. Yeah, so RC circuit was lab 8. Now we have RLC circuit, which means we have inductance now. And we did induction last time around. So now we are adding an inductor to our circuit. And this is, again, just simulation. You don't have to do anything at home. I mean, you don't have to create circuits anymore. So it's just simulation. So RLC circuit. And we already know this relationship between, well, this is Ohm's law, so we know that. And, you know, read all this, but when you have an RLC circuit or LRC, whatever you want to call it, instead of the resistance, we have something called Z, which is the impedance, which has the same units, ohms, as a resistance, but it's slightly different because now we have reactances. So reactance, again, very similar concept to resistance. Now resistance, obviously, we know that resistance is a property which stops the flow of current, or which impedes the flow of current. Now, reactance is something similar, but there are a couple of things that are different. First of all, there is no dissipation of heat due to reactances. So XL and XC. So the XL is the inductive reactance. XC is the capacitive reactance. Now these are usually defined as the resistance to flow of current through an element is called, I think, XL, the inductive reactance, and XC is and actually, you know, if you think about it, so we did inductance last time, and we looked at Faraday's law, and we looked at Lenz's law, which, because of that, we have the negative sign in Faraday's law, that the induced field actually wants to, you know, due to the change, so that induced field is produced due to the change in the initial field, but it kind of stops that. So it, you know, it stops the one thing that is creating it in the first place. That is Lenz's law. So that is the same thing. It is stopping the flow of current. So that is XL, and then I think XC is the I think it stops the change in potential difference across an element. So that is how they are defined. They have the same units. Reactances have the same in ohms, obviously, because we're adding it to the actual resistance, so they have to be the same unit. So XL, the inductive reactance, and then XC, the capacitive reactance. These have the same units of resistance. Another, and as I said, in resistance, there's heat dissipation. For reactances, there's no heat dissipation. Actually, energy is stored. And then you have a phase difference because of the reactances. So there's no heat dissipation. So those are some of the differences. And also the reactance, it can be negative, right? So XC is, as you can see, it's negative. Another way, sometimes, in capacitive reactance, you can see is 1 over omega C. Sometimes it's written as minus 1 over omega C, and then it's just XL plus XC. So actually, reactance here, it can be negative. So that's one difference between resistance and reactance as well. Okay, this should be XL. This should be an omega. There's a question mark here. Some problem, I don't know, with the equation. So this should be omega. So inductive reactance is omega L. Capacitive reactance is 1 over omega C, or minus. But since there's already a minus sign, it doesn't matter. R is our resistance, and omega is obviously the angular frequency. And I think this question mark is supposed to be a pi, because we know angular frequency, omega, here's W and here it's omega, so it's not very consistent, this document, but yeah, omega is equal to 2 pi into the linear frequency. That's also a result we know since mechanics. So these are some of the things. And then impedance, or Z, because now we also have, when there is no reactance, when there's no XL, when there's no XC, Z is equal to R, as you can see. So impedance becomes equal to resistance. But when you have these two things, then this is your equation to find Z. And then it's again Ohm's law, but instead of R, you have Z. Okay, we also have this resonant frequency. So in an RLC circuit, there is a resonant frequency. And at this frequency, the two reactances become equal to each other. And when that happens, obviously, from this equation, you will know when XL is equal to XC, they will cancel out. So Z becomes equal to R. And that is called the resonant frequency. So this is the resonant frequency. And impedance is the lowest value possible, and current is at its highest. So this is what we will be trying to find. All right, so the simulation that we have is actually, it's not something you can just, it's not a website. You have to go to the website, then you have to download this app, and then you have to have Java to use it. So you have to install Java in your system to use this. I already did, so I can, let me try share that. If I can, okay. Can everyone see this? Okay, yeah, so this is something you should see. So go to the website. Do I have it open? Yeah. So yeah. Right. So this is a link, and you just click here, you download it, and you just Google something like download Java for Windows. I use Windows. You might have a different system. And then you just download it. It's a free download, and it might say something like this type of file can harm your computer and whatnot, but I think it's safe. So you download it, and If you don't have Java, it won't open because it's a JAR file, a jar file. You need Java to open this. So, it's everything can be downloaded in 2 minutes, not a problem. Okay, let's go back to that. So you see something like this, right? And you can see where did it go? Light bulb, wire, resistor, battery, whatnot. You have everything here. Current chart, voltage chart, and you can take the AC voltage out. This is the wire. Put a resistor here, another connecting wire. You can move it around. You have a capacitor, and you can create all kinds of circuits here, basically. So what they want you to do is create a circuit with the AC voltage in series. So yeah, create a circuit with AC voltage with the resistor, inductor, and capacitor. So just put them all in there. So create an RLC circuit, and then if you left click on the capacitor, you can find out the capacitance and change it. Same for inductor and change the inductance, and same goes for the resistor. So I can try capacitor, change capacitance. As you can see, you can do that. Change resistance, you can do that. Okay. And then left click the AC voltage and change voltage, and note the current value of voltage. Change frequency, note the current value of frequency. Place voltage chart around each element in the circuit, including the AC voltage. Make sure the polarity is consistent. Okay, mark the maximum minimum voltage on each graph. Qualitatively, note the similarity differences between the graphs. What graphs are in phase with one another, which graphs are not. What about the sign of the amplitude? Okay, and using the resistance, capacitance, inductance, and the frequency of AC voltage, calculate the impedance. And place a current chart. Use the RMS current. Show that the RMS voltage from the consider the RMS current and impedance. Screen grab your circuit into the picture in the lab report. So, okay. Let's see. Current chart. We need a current. Okay. Okay, so you can see you get something. Right now, there's nothing because, well, it's not connected to anything. So if I just quickly, let's see, we get something. All right, now it's connected. So we have started to get something here. Okay, I think we need an inductor as well. And I don't think it's on the circuit. Okay. Right. You can change the frequency, you can change the voltage. Is there any change? Yes, inductor. Okay. All right, so it's giving you something. Let's go back. There's voltage chart around each element as well. Okay, make sure the polarity is consistent. So I did the current chart. We need to read the voltage chart. Just want to see if it works or not. Okay, giving us something. All right, okay. So if we change the frequency now, let's do this changes. I think we also need it around here. Okay. Right, and you'll get something like this. And obviously you need to change stuff, change capacitance, for example. Does something happen? Change resistance maybe. Okay, something is happening. Maybe the capacitor is not. All right, so you need to probably play around with it a little bit. That's giving you some values. So now once you do that, maximum minimum voltage in each graph, qualitatively notice the similarities and differences, what graphs are in phase and which graphs are not, and then you calculate the impedance and place a current chart after the voltage charts and maximum value of current. And then you need to prove this. This is, I don't know if it's actually that great. I mean, it does. Okay, you can see the voltage is 10 volts here. You can see the voltage is to be fair, you can, okay, if you click on the plus minus sign, you can zoom in here. So it's not that bad. You can zoom in. So you can see the actual values of the voltage and the current. It's not a problem. Right, so and then, yeah, include the pictures, whatever you're doing, take screenshots. In this lab, there are some problems sometimes, people sometimes your system don't play well with Java. So if you have those kind of problems, let me know. Try to install this app and then Java and see if it works. If it's working fine, you'll be able to do it. But if it's not, then let me know soon. Okay. So these are just some questions you have to answer based on this. Then the next one we have is now it's just a website, so you don't have to download anything for this. And we know the resonant frequency is given by this. And if you go to this website, so they've asked you to do resistance should be around this, capacitance, inductance, and you just put these numbers in. And you have to change frequency and try to find out which frequency you're getting the resonance. So as for VR, you have to put voltage at 2 volts overlap. You have to record current at those frequencies, and we'll set a picture. Different frequencies, voltage, current at those, inductance, current, capacitance, resonant frequency, linear, and then the angular frequency, theoretical. Okay. So this is the simulation, and then as you can see, you can change the inductance, capacitance, resistance, and here actually this little thing here tells you when you are, so Z and R, as you can see, there is a phase difference here. They're not the same, and we know at resonance these should be the same. XL is equal to XC, they cancel out, and Z becomes equal to R. So at some frequency Z is equal to R, as you can see here. And you can also see on the plot that the blue and the green waves, they're exactly opposite to each other. So it's like destructive interference, you could call it almost. So they cancel each other out. The XL is equal to XC, R becomes equal to C, and you need to do it for the values that are in the document. And you can here see you have current. So at this frequency, so this is what 330 hertz. Current is somewhere around what is this, 1.8 amperes. You need to write down these values in there. So just that is, so you do this. Okay, right, you have to record current at those frequencies. So you do it at 300, what is VR, what is current? For 400, 5, 6, 7, right? Table 2 says what is the inductance, resistance, capacitance. Once you know that, you can find the resonant frequency, which is just 1 over square root of LC. Hold on. So only one of these should be the resonant frequency, I think. And they want you to do at different frequencies, and one of them will be the resonant frequency, and I think that's what they want you to do. So, okay, you have 300, you can do 4, 5, 6. Yeah, at some point it will be equal. Yeah, it will be equal to the resonant frequency. And then you then I think you write down the inductance, resistance, and capacitance, and you find the resonant frequency, theoretical, resonant angular frequency. So one you get from the plot, and one you find out with the equation. Yeah, it's not exactly very clear, like what do you do with table 2? And it says as inductance, resistance, and capacitance. I think that is at the resonant frequency. I can only assume this is at the resonant frequency. So yeah, try these different values, 3, 4, 5, 6, 700 hertz at these values of resistance, capacitance, and inductance. Write down whatever the voltage and currents are. Then one of these will be resonant frequency. Then you find out inductance, resistance, and capacitance, which you had already set. Okay, it says put all these numbers in table 2. So, well, if they've already given you that, that does not make much sense, but okay. Calculation, then you can calculate resonant frequency, resonant angular frequency, and compare it to what you get with the equation. Is that clear? It's a bit confusing, but I think it's okay now. Does everyone get how to do this? Okay, good. I might be the only one confused here. You guys probably understand it better here. Yeah, sometimes these well, the instructions are not very clear. What to do in that case, just ask. We'll figure out some way. Okay, so yeah, after this, you could just try and download those things, and then if they work fine, if they don't, let me know. For the first part, that is. So yeah, this is your lab 10, just a couple of simulations, not much. And lab next is diffraction, and then lenses are also both just simulation. So yeah, should be fine. Questions about part 1, part 2, anything? Anyone who wants to visit the lab to do any previous experiment? No? Yeah, I'm in the lab today. There are some people here. So if you need to do something that you haven't done already, you can just let me know. I can be here next week as well. Yeah, next week, sure. Also, if you might be late responding to some emails this week, I have my defense coming up, and I've been preparing for that. And that's next week on Thursday. So till then, I might be a bit busy, but I'll still try to answer your questions, respond to your emails. So yeah, if you don't have any questions, this was lab 10, and we got a couple more left. We'll discuss the exam next week, but yeah, this will be all for today. Yeah, the lab is in Jabara Hall, if that's what you're asking. Yeah, Jabara Hall, it's 129, I think. Jabara 129. So yeah, if you're around, you can visit right now. I'm just here. I'm just sitting here. I will be here till 1:30 or 2. Okay. All right. See you.